Okay, so to recap what we were doing last time. We were starting to talk about averages. So since turbulence is a chaotic process, aka not repeatable, we need to understand it in terms of averages. And so to do that, we take different types of averages. So the first one that we talked about was a time average. And we talked about the idea of statistical stationarity. So like, does it become on average steady after a certain amount of time? And then we also talked about two different kind of time scales. So there are overall periodicity in some systems, not all, but some. And then there's also a smaller time scale, which is essentially like the micro scale fluctuations that happen. Okay, so ideally the amount of time that you're averaging over should be between those two time scales. And then if it turns out that there is no sort of overall oscillating behavior, then the kind of standard practice is to do, I think, what did I write down? 200 instances somewhere. Yeah. Okay, so that's time averaging. There is also, what's the next one? Ensemble averaging.
Everything discussion.
What?
Never mind.
Did you say
The fog averaging.
fog? What? Are you saying words right now?
No,
Hang on, I need more coffee for this. What?
No, it's because I can't pronounce words in French. Favre.
Oh, Favre.
Yes.
The Favre average
Yeah.
is not this.
Yes. Well, I know. We're not talking about a phase weighted average.
No,
Okay,
no,
my bad.
that's okay. So an ensemble average is the idea that you are going to repeat an experiment multiple times and then calculate an average based on the ensemble of all of those experiments. So the idea is it's the same thing, presumably, that you're repeating a bunch of times. And since it's turbulent, you could have slightly different outcomes each time. Okay, so this is the idea that we're going to repeat an experiment n times, and take an average over them. And it's going to look like this. So if we're still doing our average of velocity, our ensemble average, I'm going to give a subscript n. And this is just 1 over n times the sum over all of the n instances of the thing we want to average. So this is our ensemble average. This average is completely general and technically more robust than any other average. So for those of you that work with me and deal with particles, which is you, Lee.
Deal with bubbles. I don't know what you're talking about.
Okay, discrete bodies.
Kidding.
Sassafras.
I've had this morning. The sack level is up to 13 right now.
That's fine. I'll sass back at you.
That's fair. It's expected. That's all.
Yeah.
Apparently. I'm sorry.
So if you have discrete bodies in a simulation, you can do an ensemble average also over like the n bodies in a simulation. So like in our group, if you're doing like a particle laden flow, you would do an ensemble average over all of the discrete particle velocities, for example, and that's an ensemble average as well.
Okay, so that's where I was getting mixed up. So like the ensemble average would be average across all the particles, and then the Favre average would be that you're filtering it to the grid, and then your weight, you have a quantity inside of the average, and then you divide it by the average of the quantity you have.
Yes, so I will give a nod to that in a second, because I want to do the spatial average next, and then I will explain that.
Okay, sorry. I'm
Yes,
getting
no, you're
myself
fine.
Again.
No, it's fine. Because I wasn't actually going to talk about that, but I will now.
Forced her hand.
You forced my hand. I didn't want to talk about, no, I'm just kidding. I don't care. That's fine. There's also a spatial average. And that is I'm going to write it the way I have it, and then I'm going to make some notes because there are variations on this. Okay, so the spatial average, I'm going to give a subscript V for volume. But it doesn't always have to be in all three dimensions. So that's what I'm gonna kind of make a little note about. So this is 1 over the volume, the total volume, integral of over the volume of velocity, which is a function of both space and time. And essentially we just do a volume integral. All right, so couple of notes here. Or a few comments. Spatial averages don't necessarily have to be over the total volume. So I think this generalizes. I'm trying to think of a case where it would not. This should generalize. So any domain direction in which you have a periodic boundary condition is a dimension in which you can do an average. Okay, so any direction with a periodic boundary condition can have an average with respect to that dimension. Okay, so this will connect to Medita's for sure, and Jalen's work too. Yes. And Jacob's, I guess, too, by extension. Okay, so essentially as an example, if you are looking at turbulent flow through a channel that has a wave in it, you've never seen that before in your life, have you, Medita? No, never at all seen that.
Completely unfamiliar.
So this is periodic in X.
Yes, so this is periodic in this direction. So we have a periodic boundary condition in the X direction and also in the Z direction. So okay, so what this means is essentially whatever leaves the domain on the right-hand side, it gets just put right back in on the left-hand side. So this is computationally the same thing as an infinite series of little bumps in a wall that goes on and on forever and ever and ever. And then it's also something that is essentially infinitely long span-wise or wide span-wise. Does that make sense? So when we have a system like this, the turbulence in here is 3D. So we have, you know, crazy path lines happening like this, for example. Okay, so this is a fully three-dimensional thing, but we can average this spatially in both the X and the Z direction, meaning that we will get statistical data that's only a function of Y. Does that make sense? So like something like this would be generally described as statistically one-dimensional. Which makes sense, like if you remember from intro to fluids, if you were doing a problem like this, you would already expect, okay, my velocity profile is generally gonna depend on Y. And that's all, right? So that kind of extends here, except for it is fully 3D. We're just going to kind of collapse that behavior into one dimension. So this is statistically 1D, and then the spatial average is in X and Z. All right. I actually lied. I lied. This is 2D. So I overgeneralized.
Yeah, you said it was. Oh, statistically 2D.
Right, so the wave in the wall makes it two-dimensional. So like we would expect that our velocity profile will change at each X location. So we can collapse all of the fore aft stuff.
You wanted to see an example of.
Oh, yeah. Yeah, 1 second. It's gonna
Sorry.
be hard for me for the posterity of the recording unless you send me that on Slack or something.
Okay, go aside.
Okay.
If it helps. I don't
Yeah,
wanna
yeah.
derail anything.
Yeah. Right, so essentially our average. So we just do our spatial average in Z, and then we would end up with essentially velocity profiles along X, average velocity profiles along X, for example. Huh?
Seems familiar.
Oh, this is crappy of me. There's a boundary condition over here. There, imagine it goes to 0. Okay. Cool. Okay, so I just wanted to specify, it doesn't always have to be over the entire volume, because a lot of the information that we're looking for usually depends on one of the dimensions. So it just depends on the problem. Another example, Lee, did you send it to me?
I'm in the process.
Okay, can you send me a screen grab of just the picture?
Yes,
Okay.
that's what I'm doing.
Another example, and Jalen, this is relevant to your project, so,
Wanted to send the domain sketch as well. That's what was.
oh, okay. So Lee worked on a project that was Rayleigh-Bernard mixing, so hot plate, cold plate, and then you basically have free convection that causes mixing and turbulence. And so since there's those two plates there, but they're geometrically the same, so they're two flat plates. And we have periodic conditions again in X and Z. So we do the averages over those two dimensions, and then we have a one-dimensional flow there. Important to note that if you had two flat plates and you cared about an entrance length, for example, then that would be 2D as well. So you would have like the X dimension and the Y dimension that you would care about. Did you do it?
Yes.
Okay. So hang on. Okay, so this is an example of data. Actually, maybe I should show the schematic first. Okay, so this is the hot plate on the bottom, cold plate on the top. So our statistical dimension is the vertical one that we care about. And so this was curves of dissipation and TKE, right?
Yeah.
Okay, yeah. So turbulent kinetic energy, which we'll talk about in a bit, and then dissipation averaged across the horizontal direction and then the spanwise direction. So we have just like curves that go between the plates. Okay. So you'll put together plots like this. Okay, fantastic. Okay. Another thing to note about this is that this type of average has the same kind of issues as time averaging, where there are different scales and where do you do the averaging over. So this average has the same issues as time averaging relative to scales. Okay, so we call these scales lambda generally for the length scale of the turbulence. So usually this is the Kolmogorov length scale, which I'll talk about probably not today, but a later time. And we want to make sure that our volume is much greater than lambda 1 cubed, or the area is bigger than lambda 1 squared, or the length is bigger than lambda 1, right? So, and then there's also a bigger, so this is our small scale. And then our large scale is capital L. So this is the length scale of the non-uniformity. So if you have an unbounded turbulence situation, this would be like the diameter of a big vortex that exists, for example. If you have something that is wall bounded, that's kind of specified for you, so you don't have to really figure out what the large L is, because it's generally like the plate width or something like that.
Isn't the Kolmogorov scale also eta in some type of cases?
Yeah, so the Kolmogorov length scale is usually called eta.
Okay. Thank you.
Mhm.
It's all lambda, I'm like, wait.
I'm keeping it general.
Okay.
Okay, and so you want to make sure that your volume is less than this big length scale cubed. So you're doing an average over a smaller thing than the big thing, so you can still capture the big thing. In homogeneous turbulence, the large scale goes to infinity. Hey. And then we have a fun vocabulary to do. So in light of all three of these averages, there is such a thing called ergodicity. Did you laugh?
I can go a little low.
I like the adjective of it better, ergodic. It's a fun one. So this is a process in which, what?
Caitlin's face.
Jalen, do you need to step outside?
Oh, no.
You know.
You're already separated.
I know.
I don't know what more I can do.
I cannot maintain visual. I don't know what he's talking.
Now,
None
both
of
of
us
you,
can
don't
our
look at
faces.
each other.
Yeah.
Don't look at each other. So this is a process in which all the averages, so spatial, temporal, and ensemble, are properly defined and give the same result. Okay, so this is called ergodic. Ergodic. There. Okay.
Potentially dumb question. How can you have a temporal average without a spatial average?
Let me think. So that would be useful in cases where you want full field information, but you want the statistical average over time. So for example, a good example of that would be, I would imagine, I'm not in this research space, so Julian can tell me if I'm wrong. But if you were analyzing the turbulent behavior inside of an engine piston, for example, maybe that's not a great example because you might be able to do like a radial R theta. Like you could do a theta average probably because it's cylindrical. But say you had a weird geometry for like a special engine piston. It would likely be relevant to just do a temporal average. Like, so you can see over the cycles, like what it's doing
Okay, so
on average.
this would make sense in like a periodic domain where it's all just a single scalar, in which case you can't really separate the.
Yeah, so like most, I would say like most cases, the temporal average probably will not exist in isolation as something meaningful. Or at least it'll be like too much information. So,
Yeah, I guess we kind of did that in the SME paper where I had like the full field or the 2D PKE and dissipation, and then like I broke it down to the actual, like average, did the full spatial average across the periodic dimensions.
mhm.
But yeah, I guess it makes sense, just like instead of actually taking a like periodic, or taking an average across all of the different dimensions, then it's just. I think-
Yeah, so I guess like to that point, sometimes it's useful to just look at a time average if you wanted to show an indication of like the spatial fluctuations that exist.
Okay, that makes sense.
Um, but yeah, I mean, I think that that's less typical. But yeah. Oh, and I forgot. I'm gonna give a nod to phase averages. So, phase averages, sometimes called Favre average. So this is very commonly used in multi-phase simulations or turbulence. And actually it's used in the multi-phase simulations because it makes the averaged equations tidier, essentially. But what it does is it does like a phase weighted average. So if there are two phases, and I'll call it F for fluid, P for particle, then we have such a thing as, let's do alpha. So this is the volume fraction of particles. And this is the volume fraction of fluid. You can kind of think of this as like the percentage of the domain that is fluid or particle. So alpha P is just the sum from 1 to n number of particles. Volume of the ith particle over the total, oops, hang on, I don't want that in the sum. So if this is the total volume of the domain, so you basically sum up the volume of all the particles in the domain and then divide by the overall domain volume. And then because when they're added together, that should represent the entire volume of the domain, the fluid volume fraction is just 1 minus alpha P. Okay. So when we have this, the volume weighted average or the phase average or the Favre average is if we wanted to do it for velocity. So the phased average particle velocity I should say particle phase averaged is alpha P times UP divided by alpha P, where these angled brackets could represent any kind of an average. So it could be spatial, it could be temporal, it could be ensemble. And then similarly, the fluid phase average of the fluid velocity is just alpha F UF divided by alpha F. So same thing. Okay, and then I'll say mm, okay. What's wrong?
No, it make like you were writing brackets on the thing we were talking about Wednesday too, so it makes.
Oh yeah, did I?
Yeah, you did, and I was
Okay.
like, when I was like looking at it last night,
Like,
I'm
what
like,
is that?
yeah,
Now you know.
yeah, it makes sense. Also opens more questions.
Well, so actually, I like to use angled brackets for averages, but just so you're aware, some people use overbars. Which I like less, but you know.
Yeah,
And then for actually, so okay, so these are common notations. Notations for averages. And then angled brackets with like a subscript or a like tilde, like a little wavy bar over top. I'll make this of A, A. So, you know, so these are common notations for Fabre averages. Mm, I prefer the angled brackets and the angled brackets with the subscript because I find them the clearest, so. Huh?
See which phase it's.
Yeah, the little tilde. So I personally like using the tilde to represent like filtering. So if there's a quantity that's been filtered, then I'll put a tilde on it. And then the overbar is tricky. I don't mind it if it's typed. But like if I'm handwriting stuff and I want to use like an underline for vector notation, I feel like it gets a little bit confusing. Or if you're using like an over arrow for vectors and then you want to also add a bar on top of it, it's a little precarious.
In the denominator.
Huh?
That's in the denominator.
Yeah, it's like, what is this? Yeah.
The underbar is a well-bounded variable.
What? Oh, yeah. Okay, I understand. Yeah, okay. That was cute. I like that one. That's good.
He went through the check.
Oh, God. All right. I'm probably gonna mess this up. Because in my notes, my notes say change of notation. Now we're changing the averages to be an overbar. So I will keep with the brackets, but if I change to an overbar because my brain slips a gear, someone tell me, okay? Okay, cool. Okay, so now we're going to talk about fluctuations from averages. So average behavior is important, but fluctuations from the averages are also extremely important, especially for turbulence. So we'll spend some time talking about them. Okay, so in doing this, we are going to make use of Reynolds decomposition. Okay, and so Reynolds decomposition means that a full field variable is equal to its mean plus its fluctuating component. So I think we've already kind of talked about this. So this is the average. This is the fluctuating part or the fluctuation. And then this is the full field variable. Okay. Oh, and sorry, I want to go back to the Favre average. So technically, Favre averages, was that like an aggressive sneeze?
Yes.
I thought it was a cough. That's how bad it was.
Okay.
The echo definitely made it worse.
Yeah. So Favre averages, sorry, I should just add this, traditionally are a density weighted average. So let me just put this in here. Right, so this would be, you might expect, as you might expect, would be relevant for compressible flows where density is changing, right? So this is when the tilde actually makes sense. So if you're not doing this average relative to different species of like what's in the domain. So if there's only one phase, so if I have A, the Favre average is the average of rho times A divided by the average of rho. Just for completeness. Because I put my bias on it before. These are phase averages, which are basically like a Favre average where you do a density weighting, but slightly different, right? Okay. So sorry, wanted to add that. Okay, so there are a couple of important properties when it comes to Reynolds decomposition. The first one is that the mean of a fluctuating quantity is always equal to 0. So the 3 equal sign thing, that means like, always, strictly speaking. Okay. And then the second property is that if you take the average of an average, you get the average.
Broke my brain the first time I had to do it.
Really?
Well, yeah, because I think the big one was when we had 3 component and I had to do the trinomial thing and then things.
It might happen to you on homework. It's fun. It's relaxing.
Just broke my brain last night when I was like putting it in MATLAB. So I'm like, it's the same thing if I do it twice or once, so which.
You did a little proof. Look at
Yeah,
that.
exactly, unintentionally.
That's how you learn.
Past crimes that were already committed.
What?
We were doing all like KK transport stuff where I was like driving turbulent transport and like me and Will were like sitting there trying to figure out what step the error happened on.
Oh, yeah.
Not fun.
It is fun. I like doing Reynolds decompositions. It's fun. It's much better than deriving stuff in cylindrical coordinates. We could do that instead. If you prefer. So, okay, and then I'm gonna have like a little aside here. So note, this is only for Reynolds averages. These rules don't necessarily apply for filtering. So things like large eddy simulations. Okay. And I'm going to prove to you why this is the case. Small proof. It's just a little baby proof. So if I take the average of U prime, we already know that U prime is the full field velocity minus the average velocity. I guess this is another rule. So when you have the average of two things summed together, you can do the average of the things added together. So this is equal to the average of U minus the average of the average of U, which is U minus U, which is 0.
Oh, no, sorry.
No?
No, sorry, it must be equal to 0, my bad.
Wait, what?
Never mind. Just
Okay. Another way that you can think about this, and this is how I kind of always remember this, is if you think about how you've done the average over, so you're taking an average of a fluctuating thing over like a set space, time, or number of instances. So your average is always going to be central to whatever the fluctuations were. So you're always going to have fluctuations that balance each other on both sides by nature of doing an average. I feel like I made it worse, but does that make sense? Kind of.
That's how I usually think about it.
Okay, that's how I think about it too.
Yeah, but it has to be, like, there has to be an equal amount of stuff above it versus
Yeah,
below it.
otherwise that wouldn't be the mean anymore. Yeah, okay, great. Do you want to see a picture? No, you got it? Okay. Okay, great. We already talked about probability. I'm gonna recap probability because I'm gonna tie it in with averages real quick. Um, yeah, let's do that. So recall some things about probability. Okay, so I am going to define an indicator function phi. All right, and we want to assess what is the probability that U is less than some U alpha. All right, so in this case, our probability or our indicator function is equal to 1 if that statement is true, and then 0 if it is not. Right? So it turns out that the probability of U being less than U alpha is equal to the probability density function. So this is our probability density function. Which is just the sum from J equals 1 to infinity. I think it's infinity. Time rate of change, or the delta t over t, so I'm doing a temporal average here. And then this is equal to our indicator function averaged. Okay, so there's an important consequence here. Our probability distribution function is bounded. Bounded between 0 and 1. and it's also monotonic. Second. Sorry, and then I hate that notation. Mhm. Does anybody remember what symbol I gave the cumulative distribution or the CDF?
Capital,
F?
yeah, capital F.
All right, we'll keep that the same. Okay, we already kind of stated this before, but I just wanted to recap it real quick. So for example, if we have our velocity, and then this goes from 0 to 1. So this is our CDF. It'll generally look something like that. And then at some point, u plus du, we have p of u plus du. Sorry, f of u plus du. My old notes used p for both. One was like a capital P, like a scripty P. Why would you do that? Anyway, I don't know why you would do that.
It makes sense.
Yeah, wonder. I wonder. Hmm. Anyway. Okay. All right, so given this, oh wait, and then I also wanted to put one more on here, sorry. And then if we have some velocity u, was that another crazy sneeze?
The angriest sneezes ever.
See, if you're just looking at each other. For 30 seconds.
The problem is me and Jalen cannot mute our faces.
You need to be sitting like next to each other, like facing the same way. but
turn my seat.
That's the, I know,
It's fine.
a wall between them.
Yeah,
Yeah, right.
this is gonna be a problem going in.
I'll turn this car around.
You know.
No allowance.
Yeah.
Hmm?
No.
No, we got a long ways to go. 5 Bluey episodes.
How many sleeps?
Weeps. Oh my gosh. I can't tell you how many times I answered that question in real life, though.
I know, that's why I mentioned that. You mentioned about Katie, I think it was yesterday in the one-on-one, just.
How many sleeps? Okay. Let's see. So, okay, so if we want to know the probability that we have a velocity that's between u, capital U, and u plus du. So maybe I should make these capitals. These are capitals. This is the u and u plus du that I'm referring to here. Sorry for the handwriting. So this is f of u plus du minus f of u. And then if we take the limit of this thing, so if we have the limit as du goes to 0, we're approaching the condition where u is equal to capital U, right? F of u plus du minus f of u divided by du. This gives us the derivative of f with respect to U. And we call this what did I call the PDF before P?
I think it's lowercase f.
It was before? I thought it was P.
It was. Okay, never mind. No, you're right, my bad.
Was it P? It was P, right?
Yeah,
Or was it just probability? I don't know that we called it anything, did we?
at some point you drew a little arrow that said PDF.
I thought I did too. No. But I never gave it a symbol.
Oh.
What symbol do we want?
PDF.
No. That's too easy. Beta?
Sure.
Lowercase f? What do we want?
You did call it with a P up right there. Like on.
Well, wait. Hang on. I might not take it back. Hang on. Do we want P? We could keep it P. Fine. Okay, so this is our probability density function. Function. And so I think Lee said this at some point, that the PDF is the derivative of the CDF. And behold, indeed. Okay, so there's some properties for this, if you recall. So P of U is always greater than or equal to 0. And it will look something like this. So if we have U, and then, this is painful. Changing variables between like what I'm writing and what's in my notes is painful. And then that will look something like this. And then I'm going to call out 2 locations on here. So I'm going to call this A, and then this is B. If we want the probability of A or U between A and B, then this is the probability of B minus A, which is just the integral from A to B. Hang on. See, this is the problem. This is a probability, not. So it's the integral of the probability distribution function between A and B.
Just be capital F B minus F A.
I think I'm getting there. Hang on. Maybe I'm not. Hang on, just give me a second. So if we wanted to normalize this, we would use that 1 is equal to the integral from minus infinity to positive infinity of P of U du. Okay, so if we have a function f of u, what?
Sorry, this is supposed to be from negative infinity to negative infinity, or?
Oh, to positive infinity.
Yeah.
Thank you. I went rogue. It happens.
Say 1 equals 0.
Yeah.
brain shattered.
Honestly, that's where we're at right now.
You ever see that? you ever see
Divide
that-
by zero is happening all over the place.
you
Yeah.
See that one thing where it was like a massive, like, 30-page proof of like how like one could possibly equal zero or something? It's kind of BS, but it's like.
Yeah, logical fallacy, they go through one, when I was doing my discrete math class from my undergrad, they do a proof that all horses are brown, and it's so stupid.
Yeah, you can ruin everything.
Yeah.
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 Okay. So if we have a function f of u, what is the average of f of u? So we're gonna tie it all back together. Okay, so our average of f of u by definition is our integral from minus infinity to positive infinity, f of u, PDF of u, du. And the probability of f of u being between f of a and f of b is the probability of u being between a and b. As long as f is a single valued function. Okay.
Like a volume or a time normalization in either of those.
No, because average of f should have the same units as f, but like if you integrate p, that should be unitless, right? So this should still work, I think. I think. Right? I think so. I think it's okay.
Okay.
Um,
I guess it's a function of u, it's not u itself.
right. Yeah. Um, I don't know what this is saying here. I have U's that became W's here on my page, so let me just make sure that this is okay.
Maybe integration by parts at some point.
Yeah. Okay. I don't want to do this example yet because I'm not really sure where I was going with this. Okay. Let's see. Do I make use of that anywhere? I don't think so. Okay, so we can also think of our averages. Averaged quantities as the expected value. Right, because we're thinking of everything in a probabilistic sense. So that means that our average velocity is our expectation of what u will be statistically speaking. So this is equal to the integral of 0 to 1 u alpha dp. I think p. No, this was, sorry. In my notes, p is the CDF, which we called f,
Yep.
right?
Capital F.
df of u alpha. All right, which is equivalently equal to the integral from minus infinity to positive infinity of u alpha PDF u alpha d u alpha. Okay. So if we go back to our indicator function, we have that phi of u alpha is equal to 0 and 1. It's 1 when u is less than u alpha, and 0 when u is greater than u alpha, greater than or equal to u alpha. All right, and then I've already written this before, but I'm just going to reiterate. So our probability that u is less than u alpha is equal to our average indicator function on that condition. Okay, so if I draw a plot of what's going on here, so if I have, this is u, that's too big. So for example, if I have u as a function of time, and it's doing something like this, and then u alpha is right here. Then our indicator function is going to look like this. So we are looking for u less than u alpha. So my indicator function is going to look like this, where this is 1 and 0. Yes? Okay. And then this amount of time is delta T1. And then I will define tau of u alpha is equal to the sum over all of the delta t's. All right, so we're basically summing up the amount of time that u satisfies this condition. Well, this is over n events. N events where u alpha is, or sorry, u is less than u alpha during a time period capital T, okay? All right, so that means that we can write phi of u theta is equal to 1 over that time period times the sum from I equals 1 to n of delta Ti, which is just tau over T. And this is equal to f of u alpha. Okay, so then my average u is 1 over T times the quantity of the integral from u to 0, tau of u alpha du alpha, plus the integral from 0 to u star T minus tau u alpha du alpha, which gives us minus integral from 0 to u of this integral of CDF du alpha plus the integral from 0 to u of 1 minus the CDF. Okay, let's stop here because I think we're out of time. I have a little bit more, but we'll stop here. Yeah, did I make a mistake?
Balance response on the bottom one. Or it's on the left one.
Oh, okay. Thanks.
I didn't know if it was intentional or not.
My notes, I have them switched. Let me check on this.
If you switch them, you would need to remove the negative sign, right?
But the integrand changed too.
Yeah.
Let me follow up. I'll check. Okay. Okay.
Yeah, I have one question.
Yeah,
We, I think it's just like, I did a little, when we first, defined the indicator function, you made it p of t instead of p alpha.
Oh, what did I?
Below
It should be
that.
phi of t. This should be phi of t too.
I didn't know which one.
Yeah. No, no, no.
They're
It should be.
same.
Yeah. So like if you look at this plot down here, the indicator function will change with time. Thank you.
Thank you, Medina.
Yeah, I missed it.
I don't think the things are supposed to flip, because you're just putting the 1/t in there, right? You're just
Down here?
yeah, you're just distributing the 1/t, and you wrote it as equal to f of u alpha, so.
Oh, yeah, you're right. Yeah, okay. My notes are wrong then. Thank you. You're right. Oops. So this should be u to 0. Yes. And then 1/t, so 1 minus. Yes, 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 yes. Thank you. You're right.
We could just remove the negative. Look even cooler.
What?
Just remove the negative and it would.
Yeah, if you remove the negative, then swap balance back. Make it nice and shiny.
Well, I know. It's ooey. Because we'll do it next time. Don't worry.
I want it to be pretty.
You want it to be done?
Yeah, because then you can combine the intervals, right?
Well, yes, but we do more than that. There are more steps.
Like, or it's like, no, we want pain now.
Do you really? I'll keep going. Okay.